Today I'll be going over the count primes problem, and for the description you can see that it says given an integer n, return the number of prime numbers that are strictly less than n. So we can see for our input we have an integer n, and then for our output it will also be an integer because it's asking for the number of prime numbers that are strictly less than n. So for our first example we can see that for our input we have the value 10, and for our output we have 4. And that is because there are 4 prime numbers that are less than 10, which are 2, 3, 5, and 7. Now, say our input were 11, our output would still be 4 because the part that reads right here that are strictly less than n means that n isn't included in this calculation. So, since 11 is a prime number but it is not included, we would still have the 4 prime numbers, which are 2, 3, 5, and 7. And another thing to note is that 0 and 1 are not prime numbers, and that is why we'd output 0 for that. So, starting with taking care of that edge case, we could simply say if n is less than 2, return 0. And for the rest of our solution, we're going to be utilizing an ancient algorithm that was used to count prime numbers up to a range, say n, and it is known as the sieve of Eratosthenes. Now, I might be butchering the name, but it basically works like this. So we start our iteration at 2, and we go up to whatever n is. And as we go along, we remove every multiple of whatever number we start on. So when we start at 2, we remove every multiple of 2, and then we go on to the next non-removed number, which would be 3, remove every multiple. 5 is the next one, remove every multiple. 7 would be the next one, remove every multiple, and so on. Now, to implement this into our code, we're gonna say initialize prime numbers to a list of length n with all the elements set to true. And this is because we're going to be using booleans to keep track of which numbers are prime numbers and which ones aren't. So starting with index 0 up to n, we say up to length n because n isn't included. So if n is 10, we're going to have indices 0 to 9, meaning that we'll be checking those numbers as potential prime numbers. Now, true means that it is a prime number, and this is going to be important as later on um, we'll be using that to check which number is prime and which one's not, which one isn't, and to eliminate a number as a quote-unquote prime number. So we can start this by saying set prime numbers at index 0 and at index 1, because 0 and 1 are not prime numbers, to false for both. And after that, we can perform a for loop for I in the range, and we're going to be starting with 2 because that's the first number we want to check, because 0 and 1 are already set to false because they are not prime numbers. And then we're going to go up to, we're going to say the square root of n, and we want the integer value of that, and we want to add 1 to that. Now we're going up to the square root of n because it gets to a point in our iterations where we're essentially going over the numbers that were already eliminated as being non-prime numbers. So we doing this to cut the time that it will take to go over the range, and we're gonna follow that by saying if prime numbers at index I is false, we're gonna simply continue. with the loop because we do not have to check the multiples of a number that is not a prime number. Now, for a number that is a prime number, we're going to perform a nested loop. We're going to say perform a for loop, and in this case we're going to be using j in the range. Now we want to start with the first multiple of whatever number we're currently at here. So that number would be I. Now to start with the first multiple, we're going to say for, starting at I times 2, because that is the first multiple. We want to keep whatever number we are on as a prime number. And we're going to go up to n for this one, and we're going to increment by I because we're checking every multiple of it. So increment by I. And then within that for loop, simply set prime numbers at index j to false. And outside, we're gonna initialize count to a list containing all the elements that are true in the list prime numbers after we have looped through it. And then since this is gonna have the number of prime numbers that are within prime numbers, we're simply gonna return the length of count. Now to implement this, we can follow our plan and say if n is less than 2, return 0, return 0, and then initialize prime numbers to a list. We could use list comprehension for this, and we want to set every value to true for I in range n. We want to set 0 and 1 to false. So prime numbers index 0, prime numbers index 1. Both of them set to false. And then we want to loop through, saying for I in range starting at 2 up to the integer square root of n plus 1. We're going to say if prime numbers at I is false, simply continue. Else we're going to perform another loop, j in range starting with the first multiple of I up to n, incrementing by I so we could check every multiple of I. And we're going to say prime numbers at j sets false. And we can initialize count using list comprehension again. Simply say for number in prime numbers, if that number is prime, or in this case true, and then simply return the length of count. Now, if we submit this, it should work. We can see that we have a working solution. So for time complexity of this, I would say that it is something weird, something along the lines of, oh, let me type it out because it looks weird. Something like O n log of n, something like that. It's pretty weird, but as you can see, it's pretty efficient and it works. And that is my solution to the count primes problem.